Thanks. Thank you again. I will talk about old things done many years ago, but it seems it may be relatively new or even entirely new for listeners. Speaking about physics, we will talk about two problems in physics and also two problems in mathematics. You will see how are they related. We will talk about non-equilibrium physics, specifically about fast processes far from equilibrium, where interface between two phases moves fast. I ask personnel to help me. No, maybe I will do it by myself. So, first big class of problems in physics is nonlinear interface dynamics between two phases, two fluids. White color is viscous fluid, and black color is non-viscid fluid. Non-viscid fluid is applied here in the middle by syringe or whatever pump, and as you see, inviscid fluid propagates inside the viscous fluid. Because of instability, you see that after a while, in radial geometry you see fractal-like tree, in rectangular geometry you also see that. Of course, it is highly unstable and non-equilibrium process. Another classical problems, I would rather say in mathematics than physics, is the inverse potential problem, which is very important for applications in geophysics, but also as well equally important in mathematics. It belongs to classical mathematics of 19th century that started from Newton, worked seriously by Kelvin, and most seriously by Poincaré. The problem is the following. We have in 2 dimensions or in 3 dimensions matter with constant density inside a simply connected domain, which creates Newtonian potential outside in 3 dimensions, or if we replace that with logarithm in 2 dimensions. The question is to recover the domain D if what is given in a problem is U of R. If this is direct potential problem, which is just kindergarten, you solve linear Poisson equation and write the solution. Density equals 1. Inverse problem is less, much less than kindergarten. Inverse problem is to recover the domain if everything you know is far-field Newtonian potential. There are several important inverse problems which, with less or more efforts, were successfully solved. One of them, close to integrability, is inverse scattering problem, most of which solved by Gelfand and Levitan in the beginning of '50s. However, with all non-triviality of inverse scattering problem, I should mention it is linear problem. Gelfand, Levitan, Marchenko is linear integral equation. This problem is more difficult. This problem is non-linear. I can easily tell you why. Assume it is simply, assume polar coordinates. In polar coordinates, this is possible to represent, and this is exactly what we are looking for in 2 dimensions. We know U, which means we know all coefficients of multipole expansion of U. In 2 dimensions, it is just these integrals. You can easily see that where Z is, guess, x plus Iy are. So this is a moment number k, and from totality of these moments, we have to recover this boundary. How to do that? Well, I don't want to drag you in details, but everything I wanted to say is that I replace Z by R in power k exponential of ik phi. Then I switch here to polar coordinates and integrate by R. Now, because I have to find this function, you may appreciate the fact that it is really nonlinear problem. Theta phi, who cares? Now you see that you have infinitely many of these equations. You know left-hand sides, and your task is to find this function. Please agree with me that all these equations are nonlinear with respect to the function which we should find. This completes my explanation why inverse potential problem is highly nonlinear problem, which, generally speaking, doesn't have a rule how to solve it. Excuse me? Fourier transform? You consider, I cannot consider, yes, you can think that this is Fourier transform of k plus second power. Still, no chance for you, R. to find R, because totality of moments is not totality of Fourier transforms of R. Each mk is Fourier transform of only k plus second, which changes. Therefore, I repeat, no chance to recover the boundary, because it is nonlinear. If it would be linear, it would be easy, but it is nonlinear. That's everything. After this, I should remind you a bundle of physical processes far from equilibrium, which describe nonlinear interface dynamics. For instance, it is non-viscous fluid, which penetrates viscous fluid, which I showed you before. Also, any kind of solidification of liquid to solid, either in undercooled fluid or in supersaturated solution, in electrolysis, in nonlinear fractal growth, kind of I discussed yesterday, and in biological growth, where, for example, bacterial colonies spread more or less by the same mathematical description. Mathematical description is very simple, but of course deceptively simple, because serious nonlinear mathematics stands behind. After little idealization, the whole description is this. That's all. And question is, what is a boundary? A boundary of a domain omega. We have vector field of fluid velocity, and if velocity is incompressible, but with a source, for instance, at 0 or at infinity, we have this equation, and normal velocities of boundary and fluid coincide. It is the kinematic identity. That's all. From this description, we ask, what is time-dependent boundary? This is a class of free or moving boundaries. Applied mathematicians are well aware about this class of problems, which is unstable, difficult, and without analytical clue, not much can be done. However, unexpectedly, well, today it's already well expected because it's already many years since we found it, this system has infinitely many conservation laws. And these conservation laws are exactly these moments, either in 3 or in 2 or in any dimensions you wish. I already showed a week ago or so how to prove that they are constants. Probably I will not do it unless somebody feels that better still to do it if they don't know how. Do it? But you already know. Okay. I claim that this moment is conserved in time, with a single exception, and this exception this is definition of moment, right? The only exception is k equals 0. In this case, it's just volume or area which grows. Of course it grows. Moreover, it grows linearly in time. If coefficient of linearity is 1, we may say that growing volume and time, it's just the same. Therefore, this message, this theorem, merely states that all moments are conserved with exception of the lowest moment, which is time itself. If to assume, which you should not believe me without proof, that all totality of these moments can represent a boundary, and here we are back to inverse potential problem. Indeed, how could we start working on this problem if we do not know in advance that list of these moments recovers this volume? Very often it does. For instance, if boundary is analytic, it's just one-to-one, it always exists. And mathematician Pyotr Novikov proved that in 1930s. Therefore, take my words that if we know these moments, we know, not means we know, it means exists and unique, which is not of great help for physicists, but better than nothing, exists and unique, and exists this domain which we are in search of. How to prove that? Simple. If I take time derivative of this simple integral, time derivative, I replace volume integral with contour integral and integrate over the boundary. And here, normal velocity of boundary. Normal velocity of boundary, however, is negative normal derivative of phi. And I can add here phi, which is, oh, I forgot, phi equals 0 at the boundary. This is most important piece of this formulation. For example, temperature of melting is 0 centigrade at the boundary if we neglect surface tension or something like that. So I add phi, which is 0, so what's wrong to add 0, multiplied by anything which is finite. And my choice is this. Now, what you see here is a flux of this vector field, where I merely replace normal derivative by nabla. By Stokes or Gauss theorem, flux of vector field is divergence of this field, and that's all. Because divergence of this field is 0, and I hope it is clear for people that it is 0. Except Laplace of phi. If it is not 0, but instead it is delta function. However, delta function I chosen at 0, therefore if k is not 0, answer is still 0. So I proved if k is not 0, that's how it is. If, however, k is 0, it is just integral over the delta function, which is exactly 1 by definition of the delta function. So this completes proof of the fact that in this problem we have infinitely many conservation laws. All these conservation laws are polynomials in a possible simplest way of imagining what is polynomial. I can tell one interesting fact, that even if here would be not Laplace, but more or less general elliptic operator, and we probably should put it here. Lambda stands for some inhomogeneities, and U is some kind of screening or whatever potential could stand for in this field. We still have the same list of infinitely many conservation laws with a little change that instead of zk, we have here 0 modes of solutions of this equation. For example, some well-known spherical functions in 3 dimensions, or Bessels in cylindrical symmetry. So this kind of conservation laws seems to be fundamental and not at all limited to 2 dimensions or to Laplace equation. We can take a lot of advantages from this fact. After these preliminaries, let's go back to 2 dimensions. In 2 dimensions, very interesting mathematical object exists, which is of great help. This object has a name, Schwarz function. This is a closed 2-dimensional, a closed curve on 2 dimensions, and this is implicit description of this curve. I can replace Cartesian coordinates index x and y by complex coordinates, because it's better to work with complex coordinates than with Cartesian coordinates. I can name this function by something else. I can remember now implicit function theorem from the first freshman year, which tells me that at least locally I can solve this equation with respect to one of 2 letters. For example, second letter. And this is the answer of my solution. So this is solution of this equation. This solution depends on Z only, which helps to make analytical continuation, which is unique to any z outside of the unit, outside of our curve, except some singularities or cuts. Should I make it simpler, we deal here with Riemann surface. And level of complexity of this Riemann surface is given by this equation. You can replace it, as in people write in books, by second complex variable and say that we are talking about complex curve, a simple complex curve. And if we replace here this letter by z bar, so to speak, self-dual reduction of complex curve, we will have what we have. Oh, almost forgot to say, this guy has a name. His name is Schwarz function. Don't mix it, please, with the Schwarz function for construction of conformal map with automorphic functions. Even forget to think about mix with Schwarz derivative. It's just something else, but also mostly due to Schwarz. This object helps to solve this nonlinear problem which I described you. Indeed, let me make a couple of minutes for differential geometry. I want to remind you that this is a unit tangential vector along the curve. dl is just little change of arc length. Indeed, he looks along the tangent, and his length equals 1 because of that. You see that absolute value equals 1. But if you simplify this fraction, you will see this nice equation. Because instead of dz, I write here 1, and here dz bar dz, which is exactly Schwarz prime. I have a feeling that you follow. So, unit tangential vector is this. It is also clear that unit normal vector is this. Okay, differential geometry is finished. Now come back to our problem. What is normal velocity of the boundary? Now 2 minutes of kinematics. Ara, you hear me well because I am equipped with microphone, but not other way around.
Explain please the equation. Left side is vector.
Well, here I permitted a liberty that you guys can simultaneously hold in mind complex numbers and two-dimensional vectors. Okay. I hope it doesn't present significant difficulties. What is normal velocity? It is projection of velocity to the normal. Or if we switch from vectors to complex numbers, it is a real part of this product. Or if I switch here from normal to tangential, it's rather imaginary part. Because tangential is 90 degrees rotation of normal. I have a feeling that you may agree. Now, I would like to differentiate this equation with respect to time. Its full derivative. Now I would like to divide this equation over square root of S prime. Now, because S prime is dz bar over dz, it's clear that this guy is inverse conjugate. Over bar is conjugate. Now, if I transport this guy to the left, I will have imaginary part of this times 2i, because left-hand side and this guy are complex conjugate. Now you see that we are close to little secret behind this problem. This, as we proved a second ago, is unit tangential vector. This. And this is velocity. And this is velocity prime. I said enough that in the left-hand side, we got normal velocity. It is so important that I write it once again here. All right. Left-hand side is a scalar, therefore right-hand side is a scalar as well. However, this is normal derivative plus or minus, does not important now, is not important. Normal derivative of a potential. By virtue of Cauchy-Riemann, it's tangential derivative of harmonically conjugate function, which is this. Right? But tangential derivative of phi is 0, because phi does not change itself along the boundary. Phi is 0, you remember? But this depends on Z only, its holomorphic function. And by chain rule, is this, which means this. And this is again unit tangential vector. Now we equate normal velocity with what it should be. We cancel on that. And we finally got the process of moving boundary. Partial time derivative of the Schwarz function is double, I better put prime here, right? Is double derivative of the complex potential for the fluid, for the vector field of fluid velocity. This coefficient 2 is very serious coefficient. Without coefficient 2, it would be just velocity field itself. But coefficient 2 shows that something is strange and unexpected. For example, normal velocity of boundary and fluid is the same. So it is y, and this is the velocity, y2. Answer is nice. I should thank Pavel Etingov to help me to understand this answer. Answer is that if it is boundary, the physical interpretation of value of Schwarz function is Schwarz reflection, well-known Schwarz reflection from complex analysis. Therefore, if I have point which is just on boundary, the answer is Z bar. If, however, Z is not on the boundary, but not very far either, the answer is Schwarz reflection, mirror image in a sense, bar of course. And this should hold. Therefore, if my boundary moves with the velocity v, this guy should move, because this guy is constant. Better do it other way around. Put z here and put here z star bar, which by the way, z star, which by the way is time dependent, because Schwarz function itself is time dependent. Therefore, if this guy moves with velocity v, this guy should move with double velocity in order to hold this constant during my process of simple differentiation. This explains this mysterious coefficient 2. We are just one step from integrability and from showing that to skip a lot of time, because most of you heard me earlier, I would like to say that if we take advantage of conformal map, time-dependent conformal map, we can get plenty of exact non-trivial time-dependent solutions which faithfully reproduce these dynamics pictures I showed you before. And all these naive why I say naive, because it was not connected with body of integrable systems which was accumulated last 50, maybe 55 years. In this way, it was naive. Still, it was helpful to explain many interesting facts in experiments, and probably I will not speak about this today. But I ask myself often how this interesting mathematics is related to well-known integrable mathematics. With help of people who joined me later, Zabrodin from Moscow, Krichever from New York, and Wigman from Chicago, even if everyone was before in Moscow, we found the answer. I would like to show that to you. Just a minute ago, I wrote you this equation. This equation already gives you a feeling that there is something behind, because it is a conserved current. And mathematician would say that one form is here immediately, that such guy W does exist, which has this description. I hope you agree with me. Then equation 1 is nothing but compatibility of second equation. Poisson bracket and symplectic structure is already there. Don't you feel that? W is Hamiltonian, time is time, Z is coordinate, and Z bar is momentum. I hope it's clear enough from this description. Probably I better put here coefficient 2, just to be exact. In this way, this function is just but this is only beginning, because it's all about a single degree of freedom, about one-dimensional Hamiltonian particle. And here I would like to tell you something interesting. I want to remind you our moments which became remarkable, because these moments serve as conservation laws. It was the idea to consider these moments as, anyway, forget it. I just replaced one Latin letter by another Latin letter. So instead of M, I named them T, nothing else. T0, T0, is exactly our time. To emphasize this, I put here 0. Therefore, this is one form for the very specific nonlinear dynamics, where all T which are not 0 are frozen. We proved 10 minutes ago that all of them are conserved indeed. Therefore, it's nothing wrong to say what I said. They are frozen. And this is very specific, remarkable process where all of them are frozen except lowest one, which is time t itself. However, it was the idea that why wouldn't we consider the most possible general deformation of our contour, which is the most general interface dynamics. If they are most general, Tk are no longer conserved. Therefore, we can release it and now what you see describes just any kind of curve deformation. Before, it was exclusively to this remarkable process where dtk was 0 because it is conservation loss. Now, forget about Laplacian growth forever. It's just coefficient of one form. Yes. Of course, I chosen this letter for future, but I could choose any other letter. Idea is that it's just coefficient of one form. It's just coefficient. This is differential, and every letter here stands for coefficients of differential. I consider omega as a function of all t. Yes, you're right. Yes, you're right. Huh?
This way you introduced HK. HK are subject to...
Yeah, no, at this level, I just said that because omega, like Schwarz function, knows everything about a curve, everything, because it was a solution of this. Omega, which is just indefinite integral of Schwarz function, also knows everything about curves. And because in the beginning of my lecture, we already agreed that totality of moments is the same as knowledge of the whole curve, it's absolutely clear that omega depends on every body of them. And therefore, you can consider R the most general deformation of a curve and say that if it is most general deformation, generally speaking, each of moments slightly changed. And after this is just speaks nothing about any integrability, just nothing, it's just differential of omega. But because of compatibility, dhk over dtl equals dhl over dtk. Just because exact form differential, second differential is 0. Or, but this happens when h depends on z. Assume I switch from z to w. I should introduce helpful auxiliary complex plane, which conformally maps unit circle to my domain. If I do that, and by the way, logarithm of W capital is exactly W small. If I switch here from Z to C of W, this equation switches to zero curvature condition for pseudo surfaces of constant negative Gaussian curvature. It is the major point of integrable systems. I have here, after this transform, that dHk over dTk minus dHl over dTk plus Poisson bracket between Hk and HL, which means just canonical Poisson bracket because you just switch derivative with respect to Tk and Tl. I believe everybody in this room remembers that it is a classical limit of quantum picture where commutators is reduced to canonical Poisson bracket in the quasi-classical description of the system. So, after we found this interesting fact, we started to ask ourselves what kind of integrable system this description fits the best. The answer is two-dimensional Toda integrable hierarchy. I didn't plan to speak about introduction to this hierarchy, just to tell you briefly that today it is the most general kind of integrable hierarchy, such that most of known integrable systems which you heard of are most, if not all, probably all, are different reductions or limits of two-dimensional Toda hierarchy. Of course, because it is not commutator, but Poisson brackets, of course it's clear that we do not speak about full integrable Toda, but instead dispersionless limit, where h bar goes to 0. If in our picture h bar was chosen to equal 1, but you can ask me that, Mark, if you are so close to real observable physics, which represents this mathematics, what is h bar, what at least it stands for in your physical description? My answer is that at this level, I cannot answer you because it was purely classical description. However, yesterday I mentioned to you about stochastic Laplacian growth, where instead of continuous growth, where boundary attaches in continuum infinitesimal way, we assume little pieces, little particles, which just are emitted by source at infinity, and after very quick diffusion Brownian motion, they land along the moving boundary, and h bar, 2 dimensions helps here. And h bar is nothing but area of this very little particle. If this area goes to 0, but at the same time number of particles which length goes to infinity within one single time unit, such that, however, product of number of them and h bar holds to be constant and merely is increment of area, then this is exactly the classical limit. Probably I should stop here and thank you for your attention.